So here I'm going to talk about some basic non-parametric statistics. I'm doing this in my Economics 310 Stats 2. Some simple statistics. These are basically our analogs to traditional statistical methods. I'm going to do one, is going to be the Spearmint Correlation, and the other is going to be analysis of variance. And you can do it in R just with the commands, but I'm going to generate some data. I'm going to show you why you might want non-parametric statistics, and then I'm going to actually show you how you can kind of do it by hand, so to speak. You can actually use R to replicate the formula, and you'll get the same answer as you would if you just type the simpler command. So non-parametric statistics don't make any assumptions about the underlying data, particularly about the distribution of the data, which is why some people like them. They're robust to outliers, for example. They're computationally intensive, but nowadays that doesn't really matter because we all can do whatever we want on our laptop. So anyway, I'm going to generate 250 observations of random data. So I've set the seed just to make it replicable, and then I'm going to have 250 observations, and then I'm going to have a uniform distribution between 5 and 10, and this is going to give me the observations down here. And then what I'm going to do is I'm going to make a function of x, so y is going to be related to x, but I'm going to introduce some random noise so that it's not going to be a complete linear relationship. So now I've got x and y. There's a relationship there, but it's kind of noisy. We can see what the correlation is. And so if you look, here's a scatter plot. You can tell it's linear because that's what I put in here with 2.5, but it's not completely, on a straight line. Okay, so one thing you can do is the traditional Pearson correlation, and it's 0.859 or maybe 0.86, and that's pretty high. But when you do the Spearman correlation, which I show in class and in my notes is based on ranks, it's going to be close. Simply because the data are pretty nicely organized. Okay, so again, you can do the Spearman correlation by simply changing the method. If you change this to Pearson, that's the default. So if you put nothing, it gives you Pearson. This is Spearman's row. You can also do Kendall's tau, all right, which is a little bit lower in this case, but they're both positively correlated because that's how I built the data. All right. What I'm going to do here is I'm going to make an outlier. I'm going to do this with y2 so I don't delete y. And what I'm going to basically do is I'm going to take the maximum value, I'm going to multiply it by 10. Okay, and so it's going to find the maximum value, and then it takes it, and it's going to just be one huge number in there somewhere. Okay, now that actually won't change the rankings because it's going to be the top or the bottom ranked, depending on which order you're going in. But it's going to be totally different. Looking here, you can see here's my outlier. All right, so here's my nice upward slope. You can barely see it, and here's that outlier. Okay, so that's going to change the Pearson correlation because, remember, that's going to be based on deviations from means. This is going to raise the mean, but it's going to make one huge deviation in there. Correlation goes way down, all right? In class, I showed you could actually sometimes make a regression line that doesn't go through most of the data. It'll just go through this one point. Okay, now Spearman will be robust to that. Remember, that's why we like non-parametric correlations and stuff, because this one value is not going to change the rank at all. And here it's actually, I believe it's actually the same, close to the same number as before. All right, and if you do Kendall's tau, same thing. All right, so the rank-based correlation does not change. So this outlier does not matter when you do a Spearman correlation, which is what I tend to do in practice. If I do a correlation, I just automatically do Spearman. So that kind of gives the point of why to do non-parametric at all. Right? So that's the first thing, is non-parametric correlations. Second thing is I'm going to look at a measure. Basically, it's a measure that's an alternative to ANOVA, or analysis of variance. I use the Kruskall-Wallis test, which basically looks for significant differences among means in subgroups in data. And so basically, I'm going to split the data into 3 groups, and I'm going to see if the means are different. All right, so what I'm going to do is I'm going to take my data, and I'm going to put x and y, and then just some 1s in here. And then I'm going to fill in the 1s. I'm going to basically sample between 1, 2, and 3, and it's going to make groups between it will assign some of them 1, 2, and 3 in column 3. Okay, so all I did is, you can only see 3s and 2s, but there's some 1s in there too. All right, so now if we plot it, because it's random, you don't actually see much difference here at all. All right, and there might be no difference in the average here. And if we look at the 3 means, they're about 7 point something. These are probably no difference in these means because I randomly assign it. Right? So the Kruskall test, which I have here, is just Kruskall-Wallis. It's looking at this first column, which is just the x's, and I'm looking at this groups. Remember, there's going to be 3s, 2s, and 1s. Here you see, in this case, there's almost significance here. If I were to rerun this, you might actually get significance at a different level. But at 5%, this is not significant. Okay, so you can't see it visually, but this test will actually tell you that there's no significance here. Okay, Now, what I'm going to do is I'm going to make a couple of clear groups. Okay, so the next column is going to be, I believe, ones and twos. All right, and what I'm going to do is take the bottom 25%, and I'm going to assign some of those that are ones. Remember that I didn't touch that fourth column. It's going to be all ones now, but it's going to have some twos in there too. All right, so I basically took that bottom 25%, and I'm going to make it 2. Right? So group 1 and group 2, clear split, right? The top 75%, bottom 25%, which is obviously made up. You don't see that in practice, but they're clearly different. You look at the means, right? There's a huge difference between 8.12 and 5.23. You do the test here, you can see the p-value is 0, right? It's got a huge chi-square. Okay, so that's the other example. One was random, this was intentional. Now I'm going to kind of do some randomness in that last column. All right, so what I'm going to do is I'm going to take the median here, the quantile, and I'm going to assign some for 2. And then I'm going to do here, I'm going to run this loop where I'm going to take the sample in here and give some of them 1s and some of them 2. All right, and I'm basically going to sample, basically provide 1s and 2s in here. Right, so it's going to be pulling through, running this loop, and it says for some of them that are 2, I'm going to give some of them a 1. Okay, so and then for some of them that are 1s, I'm going to give them 2. Okay. So that's just some code. I made it up just to randomly assign it. But what you see here is I've got the reds and the greens mixed in now, okay, because I went in and made a column where I was kind of drawing across. Okay, it's really hard to tell, right? There's a lot of 1s that are reds or greens, and there's a lot of 2s that are reds or greens, okay? But here I'm going to make some lines. So the red mean is a little bit higher than the green mean. Okay, so let's remember the groups 1 and 2. All right, so remember this is sort of quasi-randomly generated data to begin with, so you might get a different result. All right, but with my numbers here, you can see here that it is not significant in this case. All right, and you're going to get different results with different random data. If I go back, run it again, all right, well, it's going to get the same thing because I set the seed. All right, but if you were to take that out and run it, you might get different results every time. Okay, so that can show you that it's almost significant at 10%, but we don't want to reject 10%. So you can say like, yes, they look different, but in this case it is not. Okay, if I could change some numbers, I might get a slightly bigger difference. It might be significant. Right. Now the final thing I want to do is, what about the formula? So I put this in class, then I put it in my notes. The Spearmint Correlation actually has a formula you can grind out by hand. Okay, but we're going to see that it's going to match. Okay, so I'm going to make the ranks. Remember, these are not based on deviations from means. They're based on ranking from low to high, where 1 is the lowest and then whatever n is the highest. So x1 is, these are all just the rankings in the order of my 250 observations. So the lowest is going to be 1 and the highest is going to be 250. Now, because my original x is really, look how many decimal places there are no ties. All right, in some other examples, I will round it, so you might get like a 7.6 over here, and then there's going to be a 7.6 right over here. They will be ties, and what you have to do is, if observations 9 and 10 tie, they both get 9.5. R actually will just do that for you. It'll give 0.5s to any tied observations, or if there's multiple ties, it can give a fraction. All right, so you don't really have to worry about it, but I want to show you this here. I made this up. There's 2 4s. All right, and this is the lowest number. All right, so it's going to be ranked 1. All right, but 1 and 2 are both ties, so they both get 1.5. Okay, so I just made that up to show you what happens in the case of ties. All right, so here's the rank of x, and then make the rank of y is y1, and then d is the difference between the ranks. Okay, so you're going to have a column of ranks and another column of ranks, and if they're both low ranked, d will be low. All right, and if they're both close in rank, d will always be low. But what's going to happen is, what happens if d is, you've got the number 5 ranked x and then the number 220 ranked y. All right, it's going to be a huge d. Okay, so what we do here is, you can make the difference in the ranks, and then some of them are positive and some are negative. So when I said huge d, it's huge in absolute value, right? But you could actually have a really, really small d. If they're off one direction, it could be large positive if they're off in the other direction. Right, so this is my difference in ranks. Now here's the formula I laid out in my notes. It's you take the sum of all the d squares, and then you divide by sample size as adjusted here, then the 6. This is a derivation of a longer formula that was derived a long, long time ago. If you put it in here, you get, right, remember this is the square difference in ranks. You get the same thing we had before, 0.8689, and we can test it here. exact same number. So I call this the medium way, right? The easy way is just to just churn it through R. The hard way, you'd be doing it by hand and subtracting with pencil and paper. But this uses a little bit of R, but it uses a little bit of formulas. Right? We can see where the formula comes from when we do it this way. And I like to use it just as an example. All right, we can also do the Kruskall-Wallis by hand. We saw the Kruskal test. The one thing I'm going to show you is that here's the chi-squared and the p-value. Again, not significant in the one that I ran, and that's the 3-group test from before. All right, what we're do here is we take, I use a little bit of different formula from what I put in my notes, because that is r squared over n squared. But really, if you think of r over n, that's the average, that's average squared. And then what you can do is you can actually take, basically you can have r squared over n by taking the squared average times the length. Right? So that's kind of what I do here. It's a little bit different rewriting of the formula, but it's a little bit cleaner. Right? So here I'm saying, look, here's x1, these are my ranks, and I'm saying, oh, I'm going to pick them and when this column is 1. Here's my ranks when it's 2. So this is all the average ranks for each of the 3 groups. All right, and then I take the length, like, because how many are in each group, right? So how many in 1, how many in 2, how many in 3, and they all sum to 250. All right, so they don't have to be equal because 250 doesn't divide by 3. Right, so I've got the 3 lengths here. Okay, but I've got 3 groups. So H, there's a formula I put in my notes. It's written again a little bit differently because this is the squared average, and then because the average is r over n, squared average is r squared over n squared. If you want r squared over n, you have to take the squared average and then multiply back by the length. Right, so this is the formula from my notes rewritten, and then you get the H statistic. This is the chi-squared. It's 4.862. All right, and because this is going to give me half the value, this is the chi-squared at that with this many degrees of freedom, 2 degrees of freedom. And if you see here, you have the same value before, chi-squared 4.86, and the p-value of 0.8. You see here, this just recreates. Okay, now this is easy because there's no ties. All right, if there were ties, there's a little bit of an adjuster formula that I don't really cover. But right here, I just recreated the Kruskall-Wallis. Right? So the main point here, one is that there's nonparametric analogs, or the parallel version. You can do a nonparametric correlation, and you can do a nonparametric means test. And that's the equivalent to an analysis of variance. I generate some data to show you the differences in the correlations and show what happens when there's an outlier. And then I say, well, what happens if you do 3 groups, different ways, and you can see if there's significant differences in the means. But these are good if you're worried about outliers. And then finally, I always say just do the formula by hand. That helps you learn the formula, helps you know what the computer is doing, and then helps teach you exactly why we use these statistics.